All right, good morning. Can you all hear me? Can you all hear me? Oh, okay, good. Okay. And you see a clear picture? I just worry every time I teach. Okay. So we have one more day to pick up lab kits, and I haven't been able. I don't know who has not picked up a lab kit, but if you haven't, make sure you pick one up Wednesday. Wednesday is the last day to pick up lab kits, so you need it. Okay. You need the lab kits by then. So if you don't pick them up by then you can't do the labs. And then you get zeros on those labs if you can't have the lab kits. I'm hoping you're all doing okay with Webassign. I have two kind of special assignments that I'm going to have you do. One of them has to do with learning how to scan documents with your camera into a single PDF. So I have created a camera scanning exercise. It's on Canvas. It's due on the 13th. All you have to do is download the document. You can print it out, or however you want to do it. You download the document, enter the information. It's a 3-page document. So enter the information requested, and use your camera to scan the document. So I guess you have to print it out. Use your camera to scan your document, and then convert the scan into a single PDF, and then upload it. That's all I need. That's your assignment. Okay, and the reason why I do this is because I want you to know how to do this before the exam. You wouldn't believe the stuff I would get last semester. I would get pages sideways and all kind of weird orientations and pictures that were way too magnified. It was impossible to grade on Canvas. So I have created this assignment. It's the easy assignment. All you got to do is practice to learn how to use camera scanning apps. There's a lot of apps online. One's Adobe Scan, one's Cam Scanner. Some of you guys I know are familiar with it, but not everybody is. My goal during the exams is to have you upload your exam in a single PDF file onto Canvas. Does anybody have questions on that?
Oh, I do. Sorry.
Go ahead.
So do you want us to print it out and then scan it, or you want us to do it and then print it and then scan it?
Yeah, I was thinking I'd like for you to print it out and scan it with your camera. Some people, okay. I know during the exam, some people are going to use a tablet. And
well, I usually just print it and write on it like with pencil.
Okay, and that's fine. So if you can scan it with your camera and then upload a single PDF, that'd be great.
Because I was just saying, because on the assignment, the last page says to copy and paste a picture of a scientist and then upload it.
Yeah, the whole document.
So you want us to put the picture on and then print it out and then scan it?
Yeah.
Okay.
Yeah.
All right.
Yeah, I guess so. You'd have to print it out after you've got the. Then I didn't think about that yet. You're gonna have to print it out after you copy and paste that picture. I was just choosing a random exercise just so that you have a 3-page document.
I have to wait for a printer paper to show up before we completely ran out.
Okay. So anyway, you have until the 13th for that. And then we're going to be covering a concept called Gauss's law today. I'm pretty sure we'll get to it. It's not the easiest topic in the world, although at first, but once the light goes on in your head about Gauss's law, then you'll say, how come I didn't understand that from the beginning? And so I have an exercise. It takes a little bit of work to do this exercise, but I hope it helps you to understand Gauss's law. That's the main purpose of it. And so that one's going to be due on the 16th. Again, you'll just upload it onto Canvas. So write on it, scan it, however you want to do it. Just scan me a single PDF file into Canvas. So there's an assignment created, Gauss's law worksheet. And please feel free to ask questions on that assignment because it's challenging. I mean, Gauss's law is challenging. Okay. Any questions? And we only meet once a week, so, well, we have lab, I guess. We meet twice a week. I want to make sure everybody's clear on everything.
I have a question regarding the Webassign.
Yeah.
So I purchased the multi-term subscription, I think this semester would mark 2 years ago. And so it's saying that I need to purchase, like my free trial is up and I need to purchase it again. But is that only for the Cengage Unlimited? And will I still be given access if I don't purchase another subscription?
Which assignment did you click on?
The 9th edition homework ones.
And it said you're... That's strange. Because the edition hasn't changed over the 2 years.
It says that I still have the free trial, so I was wondering, should I message Cengage directly through their help service?
Yeah, and unfortunately, they've been kind of slow.
Okay.
But yeah,
If you
go
click-
ahead. Because there's another student, same thing. Student is has a multi-term, and for some reason, it's asking the student to pay. And I haven't heard any resolution about it. I have an inside person, and I don't get any responses from the inside person. So maybe you'll have more luck.
Okay, I'll try contacting them through the direct support line.
Okay.
Have you clicked the purchase access button and see what happens?
I haven't, because I've been scared that it will cancel my last 5 days of the trial for me to finish the first homework on.
No, it doesn't.
Okay.
But what happened when I clicked it is it just automatically gave me access to the class, like it refreshed it.
Oh, okay.
So,
I guess I'll try that today after lecture.
Okay, yeah, that's a good idea. Just click on purchase and see what happens. Yeah, because I think what happens is you get choices. I think when you click on it, it'll give you a list of choices. It won't wipe out your trials.
Okay, good to know.
Okay. All right, thank you. Other questions? Okay, if you are struggling on the homework, I really hope that you ask questions. Just a second.
And people in Discord often answer too if there's homework questions.
I'm sorry?
I was saying people in the Discord often answer too if there's homework questions.
Yeah. Go
Like
ahead.
at random times.
Yeah, and I think a lot of folks are making nice use of it, and I go in and check on it once in a while, and I answer some questions. So, yeah, I like the way you guys are using it. That's great, because you're all helping each other out. Anything else? Okay. Again, please feel free to contact me if there's any issues. My concern is, one, we're online, and two, we only meet once a week, so at least for the lecture. Okay, so today what I'm going to focus on is kinematics in an electric field, and I'm not going to spend a lot of time on that. Field lines and flux and Gauss's law. This is going to be the heart of the discussion today. And I sent to you all kind of late last night a new version of my notes. I changed a few things after I did my lecture on Wednesday. hoping to make my discussion have a more logical flow at least. So you might want to follow those. So these are going to be my new version of the PowerPoint method. Just, I think I changed a couple slides. I added 3 slides in there that are more FYI, and I'll let you know when you get there. Okay. So let's start talking about the motion of charged particles in an electric field. So let's assume we have a particle under the influence just of an electric field. Then the force on the particle is just going to be Q times Z. And let's assume the particle is charged, of course. And we have a field, let's say like this. The field can be uniform or not. And if we sum the forces on this particle, you get F is Q times Z. And according to Newton's second law, if this is the only force acting on it, then this is equal to ma. And we can solve for A pretty easily. Now, if A is constant, then we can easily determine V and T. You just integrate A and you get V and T. Okay. Then we would also get the kinematic equation for constant acceleration, the exact same equations you learned in 205 in the previous course. Okay, so if you integrate this twice and A is constant, basically you're going to get the equations you learned in the previous course. The equation for constant acceleration. The only difference is that your A is going to be described by this vector, QE over M. If A depends on position, then the math is more complicated. You have to use the methods of Math 33. So if A is constant, then we'll have the following. dV over dt, Q, this is Q, E over M, and dV, Q, E over M, T, and then I integrate both sides, and I get V is Q, E over M, there's Q, plus the constant. Of course, the constant is going to be the initial velocity. This is if E is uniform. And if E is uniform, it's no different, the math is no different than the problem where you throw an object in a uniform gravitational field. The math is exactly the same. Okay. Projectile problem. This would be a projectile problem if E is constant. Okay. The only difference is in the case of gravity, this is 9.8. And in this particular case, it's just Q over M. Are we okay with that? And then if the force is constant, the electric field is constant, the net force is constant, and we want to calculate the work. The work is going to be the integral of F dot dr. And if the only force is QE, then we integrate QE dot dr. And again, if this is constant, you can pull this out of the integral, and basically you get your change in position. You get the following. And remember the work kinetic energy theorem, this is equal to delta K. So Q E, and I should be careful, times delta R is 1/2 m E final squared minus the initial squared. That's just the work kinetic energy theorem. We're going to be working with small particles like electrons and protons, and so just as a reminder, I want to give you some values that you don't have to remember. On a test, I will give you these values. Actually, I think what I'm going to do, what I will do on the exams, just to make it a little bit easier since it's online, I'll probably make the exams open book exams. So you can use your textbook as a resource. So
what are the time limits for the exams?
I'm sorry?
What are the time limits for the exams?
Oh, the times of the 3 exams?
Yeah, like how long do we have for the exams?
You'll have 2 hours.
Okay.
Yeah.
Because my biggest problem with last Physics 205 was that it's just there's too many problems and not enough time to do them.
Yeah, it's hard to do the exams online, and usually the tests are an hour and a half, right? I mean, if you were on ground, the test would be an hour and a half. We extended it to 2 hours. I think Chicago did the same thing. She extended it to 2 hours just like I have. Just so you have enough time to download the exam and upload the exam. And yeah, it can be like that in physics. Some people can get the questions done right away. Some people have a hard time finishing the exam. But I do have to establish a time limit on the exams. Okay. Let me write down the mass of the electron. And the mass of the proton. So the mass of the electron, again, is 9.11 times 10 to the minus 31 kilograms. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. So the proton is about 2,000 times as heavy as the electron. And then when we're dealing with energies, like kinetic energies of small particles, they're going to be small numbers. And so there's a unit called the electron volt that we use for energy when we're dealing with small particles. I'm sorry, I got a question in the chat about the curve for the class. Well, I guess so. I mean, we'll see how the curve works out. I did guarantee that if you're above 60, you pass anyway, whatever the curve is. Beyond that, we'll see how it goes. Okay, ouch. Anyway, 1 EV is 1.6 times 10 to the minus 19 joules. A lot of times in physics, especially my field, atomic physics, we actually convert these energies into electron volts just because we don't have to write down such small numbers in scientific notation. That's really, I think, the only reason why. We also deal with mega electron volts. Which is 1.6 times 10 to the minus 13 joules. Usually when you're dealing with fast protons that start becoming relativistic, we write the energy, the kinetic energy, in terms of mega electron volts. So these are some things you should become familiar with. You'll see these over and over this semester. Okay, these masses and these units. So I want to do an example using these ideas, and it's really related to the last homework problem. Oh yeah, by the way, before I do this example, I want to say something about the last part of the last homework problem. Because really, to me, that's a review problem, because it reviews everything you learned in the first physics course. So the people are having trouble calculating the instantaneous power on the particle. So, going back to physics 205, you know that the work done on a particle over a short distance, a really short distance, dr, is F dot dr. So the dw is F dot dr. This is in short. I can also write it in terms of the velocity at that instant. The dr, I can write it as the velocity at that instant, times dt. And dr is ddt. Then I divide both sides by dt. Use your power. Okay? Just to help you with the last problem. Another thing, or another way to write it is this. We know that the work done by the net force is a change in kinetic energy. So if that's the case, then let me take a derivative of that with respect to time. Well, what's the equation for kinetic energy? Well, it's 1 half energy squared. So I'm going to take the time derivative. And really, 1 half mv squared, really what it is this. It's a dot product of the velocity with itself. And so I'm going to use the product rule to take this time derivative. And what I'll get is this. Which gives me mv dotted with A, which is based on the net force dotted with V. Okay, so either way, you can calculate, you can take the derivative of your kinetic energy function in that problem, and you'll get your power. Okay, so I'm hoping that it helps you for the last problem on the homework. Okay, so let's do this example. So we have a particle of mass 1.2 times 10 minus 8 kilograms. We're given a charge of -1 millicoulomb, and the velocity is given as the initial velocity of the particle, and it enters a region of space that has a uniform electric field given by that expression. And I want to know the acceleration of the particle, the velocity of the particle after 3 microseconds, and we want to know the displacement of the particle after 3 microseconds. So let me start by writing the expression for the electric field. And then let me change colors. We're given that E is -6I plus 2.00J times 10 to the 4th Meters per coulomb. And we're given the mass, etc. So we know that F is QE. And according to Newton's second law, that's equal to MA. So A is Q E over N. And so now you can plug the numbers in. The charge is minus 0.001 coulomb, that's 1 millicoulomb. And if you can't see anything, just let me know. And you plug in the field. And now run out of space. And then I divide by the mass. The mass was 1.2 times 10 minus 8 kilograms. And so when you punch the numbers in on your calculator, you get A is, let me make sure the paper here, A is 5.0 I hat minus 1.7 J hat times 10 to the 7th meters per second squared. Does that sound like a large acceleration? That's a huge acceleration. And yeah, we can get small particles to accelerate to a very high velocities. We can get them very close to the speed of light. Because they're light, the acceleration on the particles can be quite large. And if you apply this acceleration, you apply this force for a sufficiently long period of time, you're going to get to within 1% of the speed of light, and that means the particle will be relativistic. You'll have to treat it as relativistic. Okay. Now what about the velocity? I just have to integrate the acceleration function. So I have to integrate ADT. And when I do that, I'm going to get the integral of this function. And of course, when I integrate, I'm going to get the constant of integration, which will be the initial velocity. So ADT, the integral is V. Of course, my constant here is my initial velocity. So I'm going to erase the C and put in my initial velocity. (3.00 I hat minus 5.00 J hat times 10 to the third. Oops. That's not negative. Now, substitute 3 microseconds. I'm going to put that here. And then I'm going to skip that step if you don't mind, and you'll get V. When you do all the math, you're going to get V equals 3.15 I hat minus 5.05 J hat, 10 to the third meters per second. Okay, any questions? Then if I want to find delta x, I got to integrate this. Okay. So the constant, I'm moving to the other side of the equation. That's why you can see a constant when I integrate this. Now when I integrate this function, v and t, now I'm not going to write units in because I'm going to run out of space. I got to integrate the whole thing. I got this. So I got to integrate this whole thing with respect to time. So, of course, you know when you integrate t, you get t squared over 2. When you integrate this term, you just get t in calculus. Typically, in this class, the integrals are not hard to do. What's hard to do is setting them up. Okay. So when you integrate this, you get 1/2. (5.00i hat minus 1.7j hat times 10 to the 7th e squared, and then you get this whole thing times 2. And this is delta x. This is not x, but delta x. That's why you don't see the constant integration rate, because I'm calculating delta x. Then you substitute. T equals 3 microseconds. And you get delta x equals 9.22i minus 15.1j times 10 to minus 3 meters. Okay, this is a simple kinematics problem. This is really a physics 205 problem.
So for a problem like this, like, can we just use the basic kinematics equations, or do you want us to show this integration? Like if we were to do it on a test.
You're fine. You can use the kinematic equation.
Okay.
I'm doing this just so that you remember how to get them. But yeah, you can do it. You can do that. That's fine. Now, if my electric field is time dependent, then you'd have to do the integration, correct?
Well, yeah.
Yeah, the electric field is time dependent. Although typically one doesn't give a time dependent electric field because they generate magnetic fields, and then you're going to have a force due to the electric field and a force due to a magnetic field. And if you want to do it correctly, okay. So generally, when you see these kind of problems in a course like this, you won't see a time-dependent field because the time-dependent field will generate another field. So if it's a time-dependent electric field, it'll generate a time-dependent magnetic field, and then vice versa. And we'll learn about that later on this semester. We'll learn about how one generates the other. So, that's really all I want to say about the kinematics. Okay, the last problem on the assignment is basically this. Okay. So, I want to talk about the concept of field lines. And so, I want to develop it quickly. I'm not going to spend a lot of time having to draw field lines, although I do feel it's kind of an important. It used to be more important in the old days because we don't have computers now. We didn't have computers in those days to be able to do the calculations that are done today. So, anyway, remember how we established the direction of the electric field? Okay, remember how I did that? I said, oh, let's say we have a positive charge in space, and I brought a test charge near it, and Anyway, there's a slide on note. I brought a slide, a PowerPoint. I'm sorry. I brought a chart near it, and I look at the force acting on the test charge, and then I divide it by the value of the test charge, and that established the direction of the field. And here's my source, and I put a test charge here, and then I put it here. I look at the force acting on this guy, and then I divide it by the value of the test charge, and then I establish the electric field. I did it all the way around the source to establish the fact that if the source is positive charge, then the electric field always points away from the source. And so wherever I put the charge, I can determine the electric field. What I'm doing is I'm able to assign a unique vector at each location in space that characterizes the condition produced by the source. A picture of that is shown here. So there's basically a picture showing the vector field. Those arrows represent the vector field. This is a vector field because at each location in space over which the field is defined, I have a vector. And notice in my picture, the further away the point is, the orange dot is from the source Q, the smaller the arrow. That's because the field is getting smaller as you get further away. Okay. So those are the vector fields. That's plotting the vector field due to a point charge. Here's another one showing you the vector field due to a dipole. So how did I get that? Well, I put a test charge at some location. For example, let me change the view here real quick. Suppose I put a point charge. I don't know if you can see the arrow, my mouse cursor moving. So let's say I put a positive point charge there. I notice that the force on it will be to the left. I divide by the positive test charge. It tells me electric field to the left. And so I draw a little arrow indicating the direction of the field. The length of it is indicative of the size of the field. And I go through every location in space and I map that out. And I get these. This is the vector field associated with the dipole. And so the dipole sets up a condition in space that looks like this, where those vectors tell you what's going to happen when I put a charge at this point. Okay. So those are the field vectors. But what if I connect those field vectors with tangent lines? Then what we're really doing is actually mapping the electric field produced by the source. And we call those field lines or lines of force. And you can actually take those field lines, and here's an example. You take those yellow lines are the field lines, which I've drawn tangent to the vector fields. Now, you go anywhere along on that yellow line, okay, and you draw a line tangent to this yellow line, it's going to tell you the direction of the electric field at that point. So these are field lines. And Michael Faraday established this idea because Michael Faraday had a hard time understanding what fields are. He wanted something more physical. And so he wasn't really that good in math, not like Maxwell. Faraday was good in the lab, but he wasn't that great in math. And so he wanted a visualization of what a field is, and he came up with this idea. So those yellow lines you see there are the field lines. And notice that as you get closer to the source, the field lines are a bunch closer together. Right, as you get closer and closer, the field lines are bunched closer together. As you get further and further away, the field lines get spread out. So and if you think about it in terms of electric field, as you get closer and closer to the source, the electric field gets bigger, the field lines get bunched together. As you move further and further away from the electric field, the field lines spread out, meaning that you have a smaller field. That's the idea that Michael Faraday used. And so he said that the number of lines per unit area passing perpendicularly through a surface is proportional to the magnitude of the electric field. By the way, the number of lines is just an arbitrary number. We'll just call it n. So for example, let me go back to the previous slide. If I made that charge twice as large, I would have twice the field. Then I would have to draw twice as many lines to indicate that I have twice the field. Okay, the number of lines isn't necessary, but the ratio of lines from one set of charge to the next is important. Because if I have two pictures, one with charge Q and one with charge 2Q, the only way to compare them is to have one picture having twice as many lines as the other. So closely spaced field lines indicate large electric field, and sparsely spaced field lines indicate smaller electric fields. And by convention here, the field lines leave positive charges and they approach negative charges. Well, it's not by convention, it's because of the direction of the field. Okay. We started with this idea to draw field lines. And really, if you want to draw them, these are some rules. Now, when you draw field lines, they really should reflect the symmetry of your system. Okay. Now, things to remember is when you draw field lines, the number of lines leaving a positive charge or headed towards a negative charge is proportional to the charge. The lines are drawn symmetrically, leaving or entering the point charge. Lines begin or end on charges, otherwise they diverge towards infinity. Again, the density of lines is proportional to the magnitude of the field. And then this is a big one that students have a hard time understanding. No two field lines can cross. What does that mean if two field lines cross? Well, it means that you have two different vectors that can represent the field at that point, and that's not possible. Right? A field, when you have a field, you have a unique vector that defines the behavior at that point in space. If you have two charges that produce an effect at a particular point in space, then you want to consider the sum of those two to represent the field at that point. Okay, you can't have two cross field lines. I mean, it's like saying I'm driving north and south at the same time. I'm sorry, I'm saying I'm driving north and west at the same time. Nobody can drive north and west at the same time. Northwest doesn't count. Okay. Any questions? So here's a picture of field lines. These are not drawn. These are actually what happens when you take two conductors and you put them in oil. The oil has thread in them. So you have threads suspended in oil. Both conductors are positively charged, or both, I mean, basically they have the same charge on them, either positive or negative. Okay. Look at the field lines, and if you notice in between them, the lines kind of repel each other. Okay, so let me kind of show you a picture what that means. So if I were to draw the field lines for that system, I would draw two positive charges. And let's say they have equal value. So if they have equal value, the two positive charges, then I have to draw the same number of lines leaving each charge. So I would do something like this. That's what the field lines would be drawn as. And that's what you see in that figure.
Real fast, Professor. So, the lines that are in the center that look like they're converging onto each other, are there technical asymptotes in between those lines that say that they never actually touch, or do they converge and, like you said, you end up drawing a summation of the two lines?
Well, actually, those two lines you see is the summation. Right? What I'm drawing there is a summation of the fields. But that is a real asymptote. They don't touch each other. They can't touch each other.
Okay, and it's the summation because the field lines look like that due to the similar effects that they're actually putting on each other?
Yes.
Okay.
Yeah, that's the sum of the fields produced by the two particles. Right? If you have two there, when you draw the field lines, you want to draw the effect of the sum of the two. Make sense?
Yes.
Okay. So let me show you one where the charges where the conductors are oppositely charged. And you see this dipole. Now, let me go back a couple of slides. Basically this, all we did was connect the lines. Oops. All right. With all my stuff running, my computer's slow. Okay, so all you see is that these vectors are connected by a line. You draw lines tangent to these vectors, and you connect them. And that's what the field lines show in that figure. Down here. Okay, so this is the dipole. The field lines due to a dipole. So I'm going to play a video. If the video doesn't work, I'm going to load it separately from. Let's see what happens.
To the ground attachment of a Van de Graaff generator, we connect a large...
Yeah, let me play it separately. Hold on a second. I thought I had the video open. I guess I don't. Give me a second. I'll open that video. I like the video. It gives you a clear indication. All right, so let me play this video.
To the ground attachment of a Van de Graaff generator, we connect a large conducting sphere. When we turn the generator on, the generator's sphere becomes strongly positive in charge, and the other becomes strongly negative. We sprinkle bits of fur into the air around the spheres. A very distinct, stable pattern appears. This pattern indicates an electric field. Notice that the field is not quite symmetrical. This is caused by the presence of other conductors, such as people, in the vicinity of the spheres.
Okay, so that you see right there is the field lines, right? You can see that how the field lines are formed. Okay. I mean, what I like about this demo, it just maps out the field lines. Okay. So let me say a couple of things regarding the field lines. Just 1 second. So I'm going to consider a point charge in space, and I want to look at the number of lines passing through the sphere of radius 1 that I've drawn, and the number of lines that pass through the sphere of radius R2. And I want to develop a relationship between the fields just from the consideration of the field lines. Since the charge is enclosed, and maybe I shouldn't have said that, but since the charge is enclosed inside both surfaces, I mean, if you count the number of white lines that go through each surface, aren't they the same? Right, I didn't draw every single line possible, right? It's an infinite number of lines, but isn't it true that the number of white lines that go through the sphere of radius R1, the green one, and the sphere of radius R2, the reddish one, don't the number of white lines pass through, or aren't the number of white lines that pass through each surface the same? And remember, we said that the electric field is proportional. Electric field is proportional to the number of lines per unit area passing through the surface. Okay, so let's start with that. The number of lines passing both surfaces is the same. Let's write that down. Really what I want to do is establish the validity of the idea of the field lines, at least in a very simple way. With a number of field lines passing through both spheres is the same. And we'll just call it n. We'll call n the number of field lines going through each one of those two surfaces. We know that E is proportional to the number of lines per area. So I want to derive an expression for the number of lines per unit area passing through R1. Okay. Or I'm sorry, I want to say something about not the number of lines per unit area, but the electric field. The electric field on the surface of R1. Remember, since we have a point charge, the field anywhere along that green surface is the same. And we know that it's going to be n over the area of that sphere, which is going to be 4 pi R1 squared. Similarly, if we look at the electric field at location 2, it's going to be equal to the number of lines per unit area on the surface of radius R2. And let's calculate E2 over E1. If I calculate E2 over E1, I get, hold on a second. N over 4 pi R2 squared, N over 4 pi R1 squared. The n's cancel, the 4 pi's cancel, and I'm left with R1 squared of R2 squared. Now, if this really is supposed to be indicative of the electric field, if the number of lines per unit area is indicative of the electric field, then when I calculate the electric field at those two locations, using the equation for the field due to a point charge, I should get the same ratio. Right? This is just from setting up a proportionality. But in reality, I know E1 is K cubed over R1 squared. I know E2 is K cubed over R2 squared. Well, let's take E2 over E1. I'm going to get K cubed over R2 squared over K cubed over R1 squared. So this ratio is in agreement with this. So this idea is really related to the electric field. And you can see that mathematically. I mean, when I first came up with it, it was more intuitive. Okay? But you can see this idea of the number of field lines per unit area is really related to the electric field, because the ratio of E2 over E1, written in terms of the field line density, is the same as the E2 over E1 that we get when we use KQ over R squared. Okay, one more thing. Again, I'm going to be playing around with these imaginary surfaces. The number of lines, I don't know the actual number, so then I don't know the proportionality constant that relates N to E and A. Like, all I can say is the number of lines passing through each one of those surfaces is proportional to E times the surface area. And again, the reason why I can just multiply E times A is because E is uniform all the way around each one of those surfaces. E has the same value all the way around that surface. E has the same direction relative to the normal to the surface, all the way around the surface. Okay. Now I want to calculate N. I want to look at an expression for N. What does it depend on? So I know that if E is proportional to N over A, then N has to be proportional to E times A. I have no idea what the proportionality constant is. Remember, N is just an arbitrary number. It's just these field lines that are flowing out of the surface. All right. Well, I know that the electric for R1, let's look at the green sphere. The field at R1 is going to be K cubed over R1 squared. And the surface area of that sphere is that. And what happens? The R1s cancel. I get 4 pi K cubed. Now I can write K as 1 over 4 pi epsilon naught. So the number of lines that pass through the green surface only depends on Q. How much charge is inside it? If there's no charge inside it, then N is 0. When n is 0, what that means is the total number of lines entering and leaving the green sphere is 0. Can I do the same thing for the other sphere of radius R2? Yeah, if I do R2, then I put R2 here and I put R2 here. They cancel. I get the same thing. So the number of lines passing through those surfaces only depends on Q. And it can be shown in general that no matter what shape you have, the number of lines only depends on how much charge is enclosed inside the surface. And it's something you'll see in more general terms in Talk 3. So, again, the number of lines, the total number of lines entering and leaving perpendicularly through any imaginary surface. Remember, these surfaces are imaginary. Only depends on the charge that's enclosed within the surface. Now, what if the field varies all the way along the surface? How do I do the calculation? See, when I did this problem, E was constant all the way around the surface. In fact, E was perpendicular to the surface all the way around it. What if the direction of E changed on the surface? What if the value of E changed all the way along the surface? Then how do I do it? I can't do this calculation. Because if E has one value here and another value here, how am I going to do this calculation? Well, I have to break it up. I have to break up my surface into sufficiently small pieces so that E is constant over that surface. Okay? So now I'm going to have to break up the surface. In other words, let's say I had a charge and I had a box. And I wanted to find the number of lines going through that box. I wanted to actually calculate. I know it's going to be Q over epsilon naught because we've established that already. But what if I actually wanted to grind through the calculation? Because the field go like this. Like these field lines don't even penetrate perpendicularly through the surface. And suppose I had this. Now what? This thing's L by L. I cannot say, oh, n is proportional to E times L squared. I can't do that because this angle is changing all the way around. In fact, the distance is changing all the way around. The value is different all the way around. So I can't do this. Okay. I mean, the angle's changing here. These angles are different. And really, what penetrates this surface is not the component parallel to the surface, it's the component perpendicular to the surface. So I actually have to figure out what is the component perpendicular to the surface that goes through. And it's going to be a different value here than here. So I have to break up my surface into sufficiently small pieces so that that component that passes through is constant over that small surface. So I got to start breaking it up into small pieces. And I got to figure out how much does each piece contribute to the total flux. I'll give you a simpler example. Suppose I have a uniform field. Okay. Let's say I have a field that's constant. And I draw a box. That's supposed to be a square, so I'll make it a square. Here's a square of size L. I want to find E times A, but I can't just do E times L squared. I can't do that. Okay. Why is it I can't do that? Well, first of all, there's no lines going from the top surface or the bottom surface. So I have to break this up into 4 pieces. So I got to find the number of lines going through here. I have to find the number of lines going through here. I have to find the number of lines going through here, and the number of lines going through here, and then add them all up. So I can't just do E times L squared blindly. I got to go around every single surface that makes up this box and figure out how many lines go through each side. In fact, the top and bottom one, no lines go through it. And in fact, on this side, the field lines enter, and on this side, the field lines leave. So I got to account for that. Some enter, some leave. So what's the total number entering and leaving? Well, it's 0. So this answer really should be 0. Because what I'm trying to do is calculate the total number of lines entering and leaving. Well, in this case, it's 0. Because here, a certain number enter, and here, a certain number leave. And do this as a square, but imagine this is a 3-dimensional box. And so what I have to do, there it is consider the component of the electric field that pierces through the surface, and I got to make the area small enough so that that component that pierces the surface is constant over that surface. Sometimes I can make that piece finite in size, but sometimes I have to make that piece infinitesimally small. What I've drawn here is the case where the area is finite in size. And so what you have to do is to get the total n is find the number of lines going on this surface, plus the number of lines going through this one, plus the number of lines going through this one, etc. And so that's why I have that summation there. And the component of the field that passes through it is determined by E dot n. So let's say instead of having an electric field that's horizontal, let's draw an electric field like this. And let me draw a box. And let me draw a normal to the surface here. So here's the field. Penetrating the surface. There's really only the component in this direction, the component in the horizontal direction that's penetrating the surface. So I have to take the dot product of E dot n to give me the component that's perpendicular to the surface. In this particular case, n points in the opposite direction of the x component, and so this will be negative. And this is always confusing for students, so if I lost that, let me know. Now, if the field varies continuously over the surface, then our delta A becomes the dA, and our summation becomes an integral. So, just saying it's E times A is not sufficient. It's really an integral of E dot dA. That's the most general way of expressing it. And if E dot n is constant, you can always pull out the integral. So, going back here, the number of lines passing through the surface in general is proportional to the integral of E dotted with a normal to the surface dot dA. And like I said before, if this is constant over the surface, I can pull it out. And then this is the area of the surface. That's what I was doing with the sphere problem. The sphere problem, this was constant all the way around the surface. By the way, I want to say something about the notation. And this depends on the faculty member. Some people will write this expression this way. Some people will write it like this. What they say VA is the area vector. Okay, they call VA the area vector. Basically, VA is n hat VA. Okay, same thing. I don't know, it's my preference. I usually write it that way. Either way is correct. Some faculty write it this way. Because it allows me to see what the dot product is, that's all. And so in general, this is the more general case, right? Writing it this way for n is the most general case. We call this thing the electric flux, by the way. Okay, this thing that we're writing down is called the electric flux. Denoted by the Greek letter phi sub e. And the electric flux is given by the integral of E dot n dA. This is the most general case. And if this thing is constant, you can always pull it out and you'll get the first term, you see it there. If the E dot n varies discretely, then you get the second equation. Okay, and then the last one is the most general case.
What is the n hat exactly?
It's a unit vector that points, well, we got to be careful. In a closed surface, it's a unit vector that points away from the surface. And you'll see why in a little bit, why we define it that way. If you have an open surface, n hat is really not defined.
Okay.
They're basically normals to a surface. And the reason why is because you need to find out the component of the field that penetrates the surface. In other words, let me give you an example. Suppose I have a pipe with water flowing in it. Instead of water flowing this way, the velocity v. Isn't it true that only the component of v that is perpendicular to this surface penetrates the pipe?
Oh, I see.
Okay, so it's the same thing, all right? You're looking at the component that penetrates the surface. It's only the component that penetrates perpendicularly that penetrates it. And so you got to write v dot n. In this particular case, you write v dot n. Here you'll do e dot n. I mean, this thing represents an outward flow of lines through a surface. When we apply this to water, it represents the flow of water through a surface.
Professor, a question with respect to the perpendicular vectors going through the surface. If it is not perpendicular, do we choose to break it into the component to make it perpendicular, or do we just disregard those vectors that are not passing through it perpendicularly?
You disregard the one that doesn't pass through, because, I mean, it's not going to cause anything to go perpendicular. So there's going to be a component tangent to the surface. It doesn't play a role.
Okay.
Only the component perpendicular to the surface plays a role. Same thing with water flowing through the pipe, right? The component of V parallel to this pipe is not going to allow the water to go through it, right?
Okay, I see.
Okay, same thing. So typically what we're interested in, at least in this chapter, is the net flux through a closed surface. And that's going to represent the number of lines leaving the surface minus the number of lines entering the surface. If more lines leave a closed surface than enter it, the flux is positive. Okay. And vice versa. So basically we're saying if the lines leave a surface, like when you have a positive charge, and we draw our imaginary surface like this, we say that the flux is positive. Well, in order for this flux to be positive, then the dot product of the electric field and the normal to the surface has to be positive. And so we define n hat to be outward. Does that make sense? For a closed surface, n is defined as outward. For an open surface, it's not well defined. You can't really define it. It can point in either direction. Okay, so let me check the time. Okay, I'm gonna talk about this and then I'll stop and take a break. So I've been alluding to fluids. I mean, this is a universal idea. It's used when you talk about heat flow. The problem is the first time you see it is with electric fields, and it's so abstract. It would be nice if you saw it with water flowing in a pipe or heat flowing through a system. Most students will see it with electric field. It makes it harder for them to learn it. So imagine the pipe you see in the figure. Let me change windows here. This is a slide I just made the other day. I hope this helps. But so imagine this pipe. It's a weird pipe because one end has a weird shape. And I want to look at the amount of fluid that passes through the left side in a certain time, delta t. I'm going to denote V as the velocity of fluid. Now, those lines that I drew, those are called streamlines. They're analogous to the electric field lines. They're basically the velocity vector of each of the particles in the fluid connected together. Okay, so those are called streamlines. So in the time v delta t, in a time delta t, that water travels a distance v delta t. If I want to figure out how much water passes through A1, I have to know the density of the fluid and the volume of the fluid that passes through. Well, the volume of the fluid that passes through is the area A1 times this distance. Area times distance is volume. So what I have here is density times volume giving me the amount of mass passing through per unit time. I'm sorry, that's not right. The amount of mass passing through in a time delta t. So I just found a mistake in my equation, sorry. The amount of mass, the amount of water passing through in a time delta t. Okay. And then I do the same thing on the right-hand side. And as long as there's no drain in the pipe, as long as there's no faucet in the pipe, the amount of water that goes in the left-hand side has to be the same as the amount of water that goes to the right-hand side. And again, because of the fact that only the component of V perpendicular to the surface causes water to penetrate A2, I write this as V2.n. This amount of water and the amount of water shown in the equation above are the same. And as long as the V's are the same through, then the amount of water here and the amount of water here are the same.
So net flux is always 0 in enclosed objects?
If there's no source or drain in there, if there was a drain,
Okay.
right? If there's like a drain inside this pipe, then you'd have less water coming out on the right-hand side. And then the two equations linking A1 and A2 would not be equal together, equal to each other. And so if there's no source, they're equal to each other. Now the fluid passing per unit area per unit time is rho V dot n. If there was a source or a drain, actually my equation is okay. If there was a source or a drain, then we would have to take into account the change in the fluid passing per unit area per unit time. And so I put that here. So this represents the fact that there's a source here. This integral would be 0 if there were no source inside. But because there's a source here, you have to have something to account for that. You got to conserve mass, okay? You got to be able to account for what's missing. Now the rho times V. Oops, there's a mistake there. The rho times V is really analogous to the electric field. The dm dt in my equation is analogous to Q over epsilon naught. So we're talking about an outward flow of something. Okay. In the case of fluid, the flux is representing the flow of fluid through a pipe. But in the case of the electric field, we're looking at the flow of the electric field lines. Much more abstract, okay? Does this kind of help a little bit in giving you a picture of what the heck we're doing? Yes, no? Okay. So let's take a break here and come back in 20 minutes and I will continue my discussion. Okay?